Hello everyone, welcome to my YouTube channel. This is Vidushi and today I'm going to explain in this video a basic KMC code to model adsorption and desorption. The code will be in MATLAB, so watch it till the end. Before proceeding forward, I will first define the problem here. We will model adsorption-desorption kinetics on a 2D square lattice. Our 2D square lattice denotes sites for atom adsorption and desorption. If a site is empty, atom can adsorb there, and if a site is occupied, atom will be able to desorb from there. In this code, we will include near neighbor interactions. That is to say, for an atom to desorb, the number of neighboring atoms and the near neighbor bonds will also be included. So now that I have described you the problem statement, I will now discuss some basics of Langmuir adsorption before moving forward to our MATLAB code. Langmuir adsorption model is the most idealistic case model where it is assumed that the adsorbate, binding atoms or molecules behave as an ideal gas at the isothermal conditions. This model is grounded on several assumptions. The most important one is that the adsorbent, the substrate here, is an ideal solid surface composed of distinct binding sites which are energetically all equal. That means the kinetics of atom binding at site A and site B will be same. Conditions apply. These conditions will be elaborated later on. To trace the isotherm, fraction of occupied sites on the adsorbent surface is calculated. Here, Vm is the total number of adsorbing sites. Fraction of occupied sites is related to the pressure of the system at a constant temperature. This curve flattens once the equilibrium is reached in the sorption process. This phenomena is temperature and pressure sensitive. Some important assumptions in this model need to be revised on which our KMC code is based upon. First, the process of adsorption and desorption is reversible. That means at any time step, bound atoms can desorb from the surface. Next, all sites on adsorbent surface are equal, as we have discussed before. All the adsorbed atoms are immobile. That means no diffusion is present in this model. In future codes, we will incorporate diffusion phenomena with adsorption. Next, we assume that no lateral interaction are occurring between the two adjacent atoms. And lastly, we only model the monolayer coverage. That means only one atom can bind at one site. As I mentioned before, these assumptions hold true in our current KMC model. So now that you know what Langmuir adsorption is, we will now use our Kinetic Monte Carlo code to solve this problem. To write a KMC code, we first need to tabulate a list of potential events in a KMC step. Here, in our square lattice, at any step, 6 events are possible. Let ij be a random location of event at any KMC step in our 2D square lattice. Left and right neighbor of point I and j are denoted by I minus 1j and I plus 1j. Top and bottom are denoted by I, j plus 1 and I, j minus 1. Remember, this is a 2D matrix, so I and j are more of x and y for the system. So if the selected site ij is empty, atom can adsorb there. This is counted as event 1 of our all potential events. We take rate of adsorption Ra as 1 per second. This is taken in this code for simplicity. Of course, rate of adsorption will vary for every system and adsorbing atom. How these rates are determined will be discussed in the following videos. Here our objective is to discuss the algorithm, and therefore we will keep rates of potential events pretty simple. Now what if this selected site ij is not empty? Then 5 set of events are possible. We will list them as event 2 to 6. Event 2 is when there is no neighbor present to site ij atom. Therefore, atom desorbs without interference of any neighboring atom. In event 3, atom at site ij has a neighbor. This one atom is present on any one of its neighboring site. In our schematic for even 3, this atom is present at site 2. This one neighbor is expected to interact with our desorbing atom. As such, its influence in the desorption rate needs to be taken into account. Similarly, in the subsequent events, even 4 to even 6, the number of neighboring atoms increases from 2 to 4. In case of even 6, all neighboring sites are occupied by atom. As such, desorption of atom at site ij will be dependent upon how strongly it is bonded with these atoms. To incorporate the effect of these neighboring atoms, we use an additional term alpha to denote the strength of near-neighbor interaction. Rate of desorption is denoted by Rd and is given by Rd into alpha to the power I, where I is the number of neighboring atoms, 0 to 4 over here. Again, for simplicity, we take the basic rate of adsorption, Rd, as 2 per second and alpha equals to 1. These values can be varied, and alpha can be varied if we need to alter the atomic bond strength. Of course, this will mostly depend upon the adsorbents. Next, we move on to define the rates in our MATLAB code. We declare a matrix R having 6 rows in one column. This matrix contains the rate of events as discussed in the form of rows. So as I mentioned, this particular code has 6 possible events. Event 1 is of adsorption and event 2, 3, 4, 5 and 6 are of desorption in the presence of neighboring atoms. This matrix, as I mentioned, contains the rate of events. R1 is the rate of atom adsorption. It's declared as 1 over here. And then R2 to 6, defined by for loop, rate of atoms, desorbing in the event 2 to 6. I minus 2 here denotes the number of neighboring atoms. This follows the previous formula of RDI equals to RD into alpha to the power I. Now before proceeding, we now define the lattice and the number of Monte Carlo runs in our code. Here, the number of Monte Carlo run n is taken to be 1000 because we aim for a simple trial run. Ideally, n should be taken very high. Ln equals to 10 defines the size of square lattice. We take our grid to be 10 by 10 in the dimensions. The next, L equals to 0, Ln plus 2, Ln plus 2 defines a special matrix L which will record the presence and absence of an atom at every location of square lattice for each Monte Carlo run. How this L will take note of surface adsorption will become more clear as we move further in our code. One important observation is that you see L matrix is not exactly Ln by Ln, but Ln plus 2 by Ln plus 2. We have added 2 extra rows and columns here. This is done to maintain the periodicity in the structure. I will elaborate this in the next section. Then P matrix stores the probability of every event for each Monte Carlo run. And last, we declare a matrix result that will store theta and t for every Monte Carlo run. As such, the length of this matrix is n. Now theta is defined before. It's the fraction of occupied sites on an adsorbent. And t will be the time of Monte Carlo run. These two, theta and t, will be stored in result and plotted at the end. Now we intend to include the concept of periodicity in our code. We consider our 2D lattice to be periodic. For this, we add 2 additional rows and columns to L matrix. As I mentioned, L matrix will store which sites on the lattice grid have atom adsorbed. Here, an atom present at location 1, 2. L matrix will replicate this result at 11, 2, as shown by the arrow here. Similarly, if an atom was present at 10, 2, L matrix will replicate that result at 0, 2. This means periodicity in the x dimension is maintained. Similarly, atoms in row 1 and 2 are replicated on y-axis. Therefore, please remember that the grid and the lattice defined remains 10 by 10. Adsorption in each Monte Carlo run happens on a 10 by 10 matrix. L matrix simply replicates results in the first two rows and columns to the two additional rows and columns, respectively. This is how an L matrix will look like. It has the values 0 and 1. So 0 denotes these sites are empty and 1 denotes the atom is adsorbed at these sites. This is an example of periodicity lattice such as graphene when the problem of adsorption was done via KMC code. Adsorption on graphene code will be discussed in the future videos, but this is how the periodicity will look like. Now we will start with our main Monte Carlo loop, but before that, we will define t equals to 0 at the beginning. So this is the time. We declare the time to be 0 before getting into the Monte Carlo loop. And then next, number of Monte Carlo runs were defined previously as n. So this loop will run from 1:n times. Before starting with the code, I will first explain the workflow within the main Monte Carlo loop. First, based upon the present state of the system, all possible 6 events and the rate of all 6 events are tabulated. That is, how many times each event can occur in this current system. Locations of each event are to be tabulated in a separate matrix. Next, the total rate of anything happening is determined, and based upon the total rate, probability of each of 6 events happening is determined. All the 6 events are then arranged in a sequence based on their relative probability weight. This is followed by choosing a random number between 0 and 1. Based on this random number, an event is chosen from the sequence of events, and this event is then executed. We update the L matrix accordingly. Lastly, the time is increased by 1 by r, where r is the rate of anything happening. Then next Monte Carlo step is executed, and again all potential events based on the current state and rates are defined. This loop runs n number of times, and theta and t for each MC step is recorded. We now declare 6 blank matrices E1, E2, E3, E4, E5, and E6. These matrices will store locations as ij, where the events are possible in the current system state. So E1 matrix will store all the empty locations. E2 matrix will store all the locations where atom is present and only one atom is present on its neighboring sites. The same way, E6 will store a location which has the atom present and all the neighboring sites also have an atom adsorbed to them. The N matrix will store the count of locations for each event. Next, we run a loop for ij to check values of ij in L matrix and tabulate ij locations in one of the events calculated. Here, the loop is run from 2 to ln plus 1. As you remember, we added 2 extra rows and columns for periodicity. Therefore, we will leave one location as dummy before and one after in the grid. For every MC step, every ij location is checked. L matrix has the values either 0 or 1 as shown, such as occupied sites have 1 and unoccupied sites have 0. So if the Lij is 0, this means the site is empty and there is a potential for event 1 to occur. Therefore, this location ij is stored in E1 matrix. But if this ij is not equal to 0, this means the site is not empty. And then one of the 5 desorption events will occur. To choose which of the desorption event will occur, E2 to E6, we calculate the number of neighbors to site I and j. It is done by determining the values of Lij in the neighborhood of Lij site. Then it is then categorized into one of the rest 5 desorption events. This is how it is done. This is a rough write-up of how this selection takes place. So if the site is empty, there is no atom present, there is a possibility of adsorption, and this location is stored in E1 matrix. Similarly, for a desorption event E2, if the atom is present at the site but no neighboring atom is there, this location is stored to E2 matrix. The same way, event E6 will be when the atom is present and has all the neighboring atoms. This location will store to matrix E6. Now the N matrix here, N1, N2, N3, N4, N5 and N6, it saves the count of E1, E2, E3, E4, E5 and E6 matrices respectively. That means N2 will show the number of locations where event 2 is possible. N1 will show the number of locations where E1 is possible. Now for simplicity in the further code, all the desorption events are put together in a single matrix called E. Now, sum of all possible adsorption and desorption rates is updated in a R matrix. This is followed by calculating the event-wise probability and tabulating probability for each event occurring in a matrix P. Here you see that P1 is probability of adsorption occurring, where R is the probability of any event happening. After this, probability of the following events is calculated and added to the probability of the previous event. By doing so, we get something like this, where the probability of P2 is added over the probability of P1. The same way, probability of P3 is added to the sum of probability of P1 and P2, and so on. This means that sum of P1, P2, P3, P4, P5 and P6 will be equal to 1. Total probability of anything happening will be equal to 1. Next, we choose a random number between 0 and 1. Now this RD is chosen between 0 and 1 as probability is always between 0 and 1. Based on this randomly chosen number, one of the probability event is selected. If RD is less than P1, then event 1 of adsorption will occur. Now the question is at which location? For that, another random number is defined and is multiplied with the total number of cases where E1 is possible, that is N1. This gives integer temp. So the location ij from E1 matrix is picked, which is a temp position. Lij is changed to 1. Subsequently, changes are also made at the periodic locations in Lij matrix if ij is one of the border sites. Now similarly for the desorption case, range of RD is chosen and even is selected. Temp number is determined and ij located at temp number in event matrix are selected. Now remember, this is a desorption case. So the value in L matrix will turn to 0 at ij. As you can see here, L, Ei, Ej is equal to 0. It is turned to 0 as the desorption is taking place. Now lastly, time and theta are updated and stored in the result matrix against the respective MC run count. Time is updated by adding 1 by r to the previous time. On the right, a schematic is shown which summarizes how the KMC event is executed. Now this MC loop, it continues for designated number of times as shown. We track the progress of Monte Carlo run in real time. As you can see in the video on the left side, after many MC steps, we get a surface coverage plot with time. It is noted that for assumed rate, surface coverage gets constant after about 0.5 seconds, as you can see here. So this gives the surface coverage of 2D square lattice in the case of adsorption and desorption. Of course, this plot will vary when we change our RD and RA. and also alpha taken in this code. This code is also available in a book, Molecular Simulation Methods in Mechanics and Physics, in segment 6. First draft of this code was written by Dr. Dibakar Datta, who is also my PhD advisor. Link to his website is given below in the description section. So this was Kinetic Monte Carlo code to study adsorption and desorption on a 2D square lattice. In further videos, I'll extend this work and this code to other 2D materials such as graphene. So please stay tuned and subscribe.